Good morning, students. I, Professor Arvind Mudhedhar from Department of Mechanical Engineering, welcome you to the subject Design of Machine Elements 1. Today, let us see the problems on element subjected to biaxial stresses along with the shear stresses. So, in this first problem, let us see the problem statement here, where in the figure you can see that the element is subjected to the biaxial stresses along with the shear stresses. So problem statement, here we have a point in a structural member subjected to plane stress is shown in figure. Determine the following. The first one, normal and tangential stress intensities on plane MN inclined at an angle of 45 degree. So this is the plane MN, which is inclined at an angle of 45 degree. So on this plane MN, we have to find the normal and the tangential stress intensities. The next one is principal stresses and their direction. So we need to find the intensity of the principal stress and its location. And already we have studied what is principal stress. It is stresses which is acting on a plane with a zero shear stress. Such a plane is called as principal plane. The stress acting on that is called as a principal stress. So we need to find such a principal stress intensity and its location. The third one is maximum shear stress and the direction of the planes on which it occurs. So next thing we need to find what is the intensity of the maximum shear stress and its location. So here we have the element which is subjected to biaxial stress along with the shear stress. So this is sigma x, which is acting in the tensile direction or the tensile mode. So sigma x value we have 40 megapascal, whereas sigma y you can see it is in the compressive direction. So we can consider it as a compressive load, and the stress is sigma y is equal to 30 megapascal, and we have the shear stress which is of 25 megapascal, and here we have the plane MN which is inclined at an angle of 45 degrees. So first we need to find the normal stress on the plane MN. So I would like to tell you that for this you have to refer the data handbook. Okay, the soft copy of the first unit of the data handbook I will put into the WhatsApp group. So please refer that if you don't have the data handbook, and I suggest you to purchase a data handbook as early as possible to go through these problems, because without the data handbook we cannot solve the problems, and the data handbook is allowed in the examination. You have to refer the data handbook. So as early as you buy and start referring the data handbook, you will feel comfortable in the studying the subject, else it will be quite difficult to understand the subject. So I am referring the data handbook K. Mahadevan and Balvi Reddy. Whatever the equation number I write in front of the equation, so that will refer to the data handbook K. Mahadevan and Balvi Reddy. Okay, so we'll start with the first one, normal stress on the plane MN. So from equation number 1.8a from the data handbook, we have sigma n is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos theta plus tau xy into sin 2 theta. So we substitute the values here in this equation. Sigma x we have 40 megapascal, and sigma y I have written it, the magnitude of the stress 30 megapascal. Since it is compressive in the nature, okay, you can see in the figure sigma y is compressive in the nature, we consider it as a negative. So it is minus 30 divided by 2 plus sigma x value is 40, sigma y value is minus 30, so minus minus will become plus, so it is plus 30 divided by 2 into cos 2 theta. So we are finding the normal stress on the plane MN, which is inclined at an angle of 45 degree. So we consider theta is equal to 45 degree. So it is 2 into 45 plus the value of shear stress is given as 25 megapascal. So it is 25 sine into 2 into 25. So after solving this equation, we will get normal stress sigma n as 30 Newton per mm square. Next we have shear stress on the plane MN. So from the data handbook, the equation number 1.8b to refer, we have tau n is equal to sigma x minus sigma y divided by 2 into sin 2 theta minus tau xy into cos 2 theta. So substituting the values of sigma x and sigma y in the equation 1.8b, okay, so we get the shear stress on the plane MN, which is 35 Newton per mm square. So these are the normal and tangential stresses acting on the plane MN. So sigma n is known as the normal stress acting on the plane, and tau n is known as the tangential stress which is acting on the plane. Next we have principal stress and the direction. So from equation number 1.8c, we have sigma 1, the principal stress, sigma 1 is equal to sigma x plus sigma y divided by 2 plus root of sigma x minus sigma y divided by 2 whole square plus tau xy square, from equation number 1.8c. Again substitute the values of sigma x and sigma y. So just remember, sigma y in this problem, it is compressive in the nature, therefore we consider it as a negative. So 30 minus 30 divided by 2 plus, substitute the values here again, minus minus will become plus, tau xy value is 25, you will get maximum principal stress as 48.0116 Newton per mm square. Similarly, we have minimum principal stress from equation number 1.8b. The only difference between 1.8c and 1.8b is plus and minus between these two parameters. For minimum principal stress, it is negative. So again substituting the values and calculating, we get minimum principal stress as minus 38.0116 Newton per mm square. Next we need to find the angles at which these principal stresses acts on the plane. For this you refer the equation number 1.8e. So here equation is tan 2 pi 1 is given, okay. So these symbols will change according to our convenience, okay. So we write it as tan 2 theta 1 dash is equal to 2 tau xy divided by sigma x minus sigma y, as given by equation number 1.8e in the data. So for finding the theta 1 dash, bring this tan theta and this 2 on this side. So equation is rewritten as 1 by 2 tan inverse of 2 tau xy divided by sigma x minus sigma y. And theta 1 dash and theta 2 dash are 90 degree apart, which is given in the data handbook itself below the equation number 1.80. So please refer the data handbook. So substituting the values, we get theta 1 dash is equal to 1 by 2 tan inverse of 2 into 25 divided by 40 plus 30. We get theta 1 is equal to 17.769 degree and theta 2 is equal to 107.769 degree. So this plus 90 degree will give this result. Okay, so here as it is written theta 1. Okay, theta 1 is nothing but theta 1 dash only, and theta 2 is nothing but theta 2 dash only. Okay, so don't get confused regarding this. So you can use either of the symbol. Just keep the similarity in the symbols. Okay. So next, coming to the third point, maximum shear stress. From equation number 1.8 we have tau max is equal to plus or minus root of sigma x minus sigma y divided by 2 whole square plus tau xy square as the equation, and which is also equal to sigma 1 minus sigma 2 divided by 2. Okay. So referring to this equation, here we have sigma 1 value as 48.0116 Newton per mm square. So which we have calculated earlier. Here you can see sigma 1 value, and this is sigma 2 value. Substituting these two values here in this equation, we get tau max as 43.0116 Newton per mm square. So now we need to find angles at which the maximum shear stress acts. So this is the intensity of the maximum shear stress. We need to find what is the location of this maximum shear stress. So which is given by theta s max, that is angle of shear stress, maximum shear stress is theta 1 plus 45 degree. So this is angle of principal stress, theta 1, which we have calculated earlier. So theta 1 as 17.769 and theta 2 as 107.769. So maximum shear stress angle is theta 1 plus 45 degree, which will give us as 62.769, and minimum shear stress angle theta s minimum is equal to theta 1 plus 135 degree, which is equal to 17.769 plus 135. So it will give us the angle as 152.769 degree. Okay. So again this theta 1 plus 45 degree and theta 1 plus 135 degree, you can find this in the data index below the equation number 1.8g. So this is the solution for the first problem. Here I will just again review the results for you. So normal stress and tangential stress on the plane MN. So sigma n is the normal stress and tau n is the tangential stress on the plane MN. Next, principal stress and their direction. Sigma 1 is the principal stress, that is maximum principal stress. Sigma 2 is the minimum principal stress, and its location is calculated here as theta 1 17.769 and theta 2 as 107.769 degree. And third, we have maximum shear stress. So tau max is the maximum shear stress and its location we have calculated. So this is the solution for the first problem. Next, let us start with the second problem. Here in the figure you can see element is subjected to tensile stress and shear stress only. There is no compressive stress or there is no stresses in the y direction. Along with this tensile stress, we have the shear stress which is acting on the element. So let us see the statement. The state of stress at a point in a strained member is shown in figure. The tensile principal stress is known to be 84 Newton per mm square. So here in this problem they have given the intensity of the tensile principal stress, that is sigma 1, okay, not sigma x. Sigma x is the stress on the element in the x direction, and here in this problem they are giving us the data of principal stress, tensile principal stress. So that is sigma 1 is 84 Newton per mm square. Continuing the statement, determine the first one, maximum shear stress at the point and orientation of its plane. So we need to find the maximum shear stress and its orientation, and shearing stress acting on the element. The second one is shearing stress acting on the element. Okay, so these are the data we need to find. So let us see with the solution. So let's first find out the maximum shear stress, that is tau xy. First let us find this the shear stress. So here we have the equation for tensile principal stress from the data handbook, equation number 1.8c. Sigma 1 is equal to sigma x plus sigma y divided by 2 plus root of sigma x minus sigma y divided by 2 whole square plus tau xy square. So this is the equation given for principal stress, maximum principal stress. In the given data, we have the value of sigma 1 as 84 here, and sigma x value is given to us, that is 55 Newton per mm square. And since we don't have this sigma y, so that value we consider it as a 0. So when you substitute these parameters in the equation 1.8c, the only unknown in the equation is tau xy. So this is the shearing stress on the element. So by solving this equation, we get shearing stress tau xy as 49.356 Newton per mm square. After this, we find out maximum shearing stress. So maximum shearing stress is given by the equation tau max is equal to plus or minus root of sigma x minus sigma y divided by 2 whole square plus tau xy square. So this is given by equation number 1.8f. 1.8f. Substituting the values here, sigma x 55 and tau xy as 49.356, sigma y is not given, so it is 0. We get maximum shear stress as 56.5 Newton per mm square. So we need to find the angle at which the maximum shear stress acts. So for this we have equation 1.8g, tan 2 theta 1 dash is equal to minus of sigma x minus sigma y divided by 2 into tau xy. So it is given by equation number 1.8g. So in the previous case, okay, in the previous problem we had the value of sigma 1, sigma 2, and with the help of that we used to find the value of angle of principal stress, that is theta 1 and theta 2. Later, with the help of this theta 1 and theta 2, we used to find the value of maximum shear stress location, that is theta s max. We used to find in this way. But in the present problem, we don't have the value of this theta 1 and theta 2. Okay. For that reason, okay, we are using this equation here 1.8b with the negative symbol. Okay, use with the negative symbol. So you will get it as theta 1 dash as, or you can also write it as theta s max is equal to minus 1 by 2 tan inverse of sigma x minus sigma y divided by 2 tau xy. So substitute the value of sigma x as 55, sigma y as 0, tau xy as 49.356. Yeah, 49.356. You'll get theta 1 max as minus 14.563 degrees. So this is the angle of maximum shear stress. So this theta 1 dash is nothing but theta s max, which is mentioned earlier in the previous problem. Okay. Next, direction of minimum shear stress, we can write it as theta 2 dash is equal to theta 1 dash plus 90 degree, which is equal to 75.437 degree. So this is the solution for the given problem. So in this problem, what you have to notice is for finding the maximum shear stress, we don't have the value of sigma. We don't have the value of theta 1 and theta 2, that is angle of principal stresses. We don't have. Okay. So without that, only with the help of this parameter, we are finding the value of the angle of maximum shear stress and minimum shear stress using this equation 1.8b with a negative symbol. So, and you will get the theta 1 dash. For this, you have to add 90 degree. So, there you will get the direction of minimum shear stress. So, this is the solution for the given problem. Thank you.